Hi everyone. In this video we're going to start or begin to talk about chapter number 3, which talks about discrete random variables and probability distributions. Okay, so discrete random variables and probability distributions. We first have to try to understand what those are and how those fit in and help us um, go about understanding probability and understanding the real world with probability. So first we're going to talk about what a random variable is. And a random variable is going to be essential uh, to us moving forward in really um, all of our probability chapters and even beyond then. And so we really need to understand this probabilistic structure or this tool that we're going to use, which is a random variable. Okay, and so after we understand what a random variable is, then we'll talk about the basics of discrete probability distributions. So they have something to do with random variables. They actually describe them, and we're going to talk about the basics of them. Okay. Then we'll talk about moments and whatever the heck moments are. Then we'll talk about specific probability distributions, and these are the specific ones that we'll talk about. Now, that's the outline for the whole chapter. It'll take us multiple weeks to get through this chapter. In this one, we're only going to begin to talk about random variables. So, start section 3.1. Basically, what my sort of paragraph or long sentence here is trying to say is that before, what we've been working with were Venn diagrams, situations in which we can easily come up with probabilities about elements of a sample space. Okay, but in order to do more sophisticated stuff, we need to actually come up with this new structure that is going to help us in more complicated problems. And so when we want to consider probabilities about events that aren't equally likely and aren't set up in a way that makes calculations easy, like Venn diagram-ish type stuff, we need to introduce a more formal probabilistic structure. Okay? So that structure is a random variable. And as the name states, it is random and it is variable. Okay, so a random variable is a variable because different numerical values are possible. Okay, so a random variable is always going to be numeric. So it's always going to be a number. It can be an integer or it could be a decimal. Okay, but it's variable because we sort of it's not a single value. It is variable. Okay, and it's random because the observed value depends on which of the possible outcomes occurs. So we don't know the value of it beforehand. Okay, and so it is random. So we got a random variable, and that's going to be our basic probabilistic structure that we're going to use. And technically, mathematically anyway, a random variable is actually a function. Okay, and so this picture gets at what the random variable is trying to do. Okay? So on the left, we have our sample space, our usual rectangular picture with our script S in the bottom to denote the sample space. And what the random variable does is it takes elements of the sample space, and so you can think of the sample space in any way that we've sort of defined before. Okay, any example, think of that concretely in your head. Okay, and a random variable is a function that takes in that element from the sample space and then outputs a number on the real number line. Okay, so it's a function from the sample space to the real number line. And so it's to the real number line, or real numbers are nice to work with. Okay, and we can quantify them. We know the distance between real numbers, so on and so forth. So for many nice reasons, it goes to the real number line, and really, theoretically, there are very, very sophisticated and sort of like graduate level math and stats that go into the definition, the real definition of a random variable, but this is sort of good enough for us to move forward. And so here's a little bit of it. Mathematically, a random variable is a function from the sample space to the real number line. And that's what this picture is showing. So that's great, but what actually is a random variable is going to be easiest for us to understand by just looking at some examples. Okay, so if my experiment that I'm doing is flipping a coin once, I have two possible outcomes, heads or tails. And so what a random variable is going to do is it's going to map that either heads or tails onto the real number line. And what we usually do is we're going to map one of the values to 0 and the other one to 1. And so you'll notice, I don't formally say it, but you'll notice anytime I talk about a random variable, I use a capital letter, a capital Roman letter, usually X, okay, or Y, to denote that random variable. So we always use capital X and Y to denote that. And so if X equals 1, then it's heads, or rather if it's heads, then X equals 1, okay, and 0 when it's tails. And so that's a function. You put in either heads or tails, and then out pops either 0 or 1. That's sort of the definition of a function. Okay, take something in and then give something back. And it's something that maps us from the sample space to the real number line. Okay. Now, another experiment that we're actually used to, we've talked about before, that if we roll two fair six-sided die together, okay, or sequentially, doesn't really matter. If my random variable is the sum of the two die, okay, that's one possible random variable that I could come up with for that situation. And so that maps, the two faces to one number on the real number line. Okay, so possible outcomes could be 1 and 6. The random variable function is going to take in that 1 and 6, and then the output of that function is going to be 7. And a sort of another different example that takes in and spits out possibly more values is if my experiment is running a marathon, okay, a random variable could be the time in seconds it takes to complete that marathon. This is an example of a random variable that has lots of possible outputs. So for our first two examples, the first one only has 2 outputs. The second one has anywhere from 2 to 12 outputs. It was an output of either 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. Okay, but the third one has an infinite number of sort of outputs. So X could be an infinite number of numbers. Okay, so it could take, although not humanly possible, it could take 30 seconds to complete a marathon. Or it could take, 5 years to complete a marathon, so on and so forth, theoretically. Now, there are some bounds, of course, but we aren't going to worry about that. So that random variable is quite different than the first two that I showed you. And then a fourth example here, observing customers at a business. So maybe I'm at my place of business and I want to sort of track how my customers are behaving. I could be interested in the time it takes between two customers entering the store. So maybe I'm interested in how much traffic is going on throughout the store, or I'm trying to track how many people come in the store, and so I might be interested in the time in seconds it takes between the two customers to enter the store. Okay. So a quick side note is that we may actually be interested in multiple random variables about the same experiment or situation. So For that last experiment, observing customers at a business, I can be interested in the time it takes between two customers to enter the store as a measure of like traffic, but I can also count the number of um, customers that come into the store within an hour's time. Okay, two different variables, two different random variables about the same situation. Okay, so moving on, when a random variable only has two outcomes, it's characterized as what's called a Bernoulli random variable. Okay, as a side note, the Bernoulli family was a very powerful mathematical family in Italy in the 16 and 1700s, I believe. But one of them or all of them came up with this sort of idea, or it was at least attributed to them. So two outcomes, which is what we saw in our first example of a random variable. So a few notes about Bernoulli random variables. No matter what the background of the problem is, I'm always going to call the outcome that corresponds to a 1 as a success and 0 as a failure. Okay, and so a possible experiment is to see how long cancer patients live or if they recover from cancer based on a drug or something of the like. And a successful, but certainly not in this case that I just described, but a successful outcome could be death. Okay, whereas an unsuccessful outcome could be, continue to living. So it is possible that I could say 1 is death, 0 is living. And so technically I'd call death a success, even though no one in their right mind is going to say death is successful. Okay, but in this sense, in this sort of structure, that's what we're going to do. Okay, is keep that no matter what the background of the problem is, if it makes sense in our minds operationally. Okay. So Bernoulli random variables are extremely important, and they are the building blocks of other important random variable types. And we won't see that for a while, but when I get there, I'll of course remind you of Bernoulli random variables. Okay, so our first your turn is for you to come up with 3 different types or 3 different examples of a Bernoulli random variable. Okay, so you can think of a situation or multiple situations and then come up with Bernoulli random variables about those situations.